Okay, it's 10 after time to start up. Hopefully your day is going well. Like in a regular classroom, this is where normally students will like look up and mumble something. With the whole Zoom thing from, it feels so 2 years ago, but whatever. The real issue is, well, this is what we're doing right now. And I do hope that your day is going well. And I promise that when I see you on campus next fall, I will be surprised that some of you are much taller than I expected, and others of you will be much shorter than I was expecting you to be. It was supposed to be funny. Of course, some of you won't recognize it all because you're not currently showing your picture. And I find it really beneficial to have y'all showing yourselves. So that way, again, if I see nods or a thumbs up or something like that, that's great. If I don't see those things, I'm still going to do what I'm going to do, but I'm going to do it without feedback. And the feedback allows me to pace myself better. It allows me to sort of see if I need to reemphasize the point. It's a good thing. So thank you for those of you who can be weasable. Okay. So time to start up. And I always like to start with any questions on administrative matters. I do appreciate one of you sending an email saying, please put up the notes from Tuesday. And I did, but later than I intended to. Sorry about that, but they're there now. And the notes for today and Thursday's class session already there. So I felt good about myself that at least, they weren't missing. Second, I do think I correctly put some homework stuff that's due next week online already. And a lab activity for the day today, and that will be due on tomorrow at 11:59 p.m. Okay, so let's talk about homework just real quickly. The homework that corresponded to class yesterday will be due tonight. So you always will have a chance to ask a question in class before homework's due. The problems that match the stuff we're going over today and on Thursday, yeah, you could ask about some of those homework questions in class tomorrow. But if you don't get around to it until, Friday to get to those problems, you'll still have a chance on Monday to ask questions about those homework problems. So it does push the homework back just a little bit in terms of on Mondays turning in it later. That would allow you to get prompter feedback, but the ability to ask questions of yourself, of others in the class, and then get hold of me during class on those last few things that you're not so sure about. That's good, in my opinion. When you do turn in the homework by tonight, 11:59 p.m., if I have the ability to have the answers online by then, I will do it. So that way you can then look immediately. But more likely it's going to be tomorrow morning by about 8:30 that the homework answers would appear. Okay. Same deal for the homework to be due Monday night, 11:59. You can expect by Tuesday morning to see the homework answers for those problems appearing. So administratively, I think I touched on most of the things I wanted to mention. Did any of you have administrative questions? Okay. Yeah, a good question. There is a lab that's due today. The lab that we did yesterday is due today on Canvas. Hopefully, the lab that corresponds to today's class is due tomorrow, but I will check the date on that. Certainly, if the date is not for tomorrow, it should be reset to that. So whatever we started on today in the lab on analysis of variance, I get it done by Thursday at midnight. So thank you for mentioning that. Okay, any questions on subject matter? And I know there should be at least one good question on the subject matter, probably two.
I have a question.
Go ahead.
You can go first.
Okay, really quick. I just had a question on the Finch data. Did we need to make that binary, or do we keep it as it is?
Yeah. So I'm going to share a screen, and probably I'll just share a screen for the rest of the whole hour. Yes, good, go share. And jump over to GMT and I thought I had it so the Finch data would pop right up, but you know what? Okay, I'm going to go and look for that Finch data somewhere else and reopen. So yeah, you're correct to note, and it's opening now. I wonder if it's below something. Oh, it was hiding behind the chat. I'm sorry, I didn't see that it was hiding behind the chat. So the Grants Finch Beak data, you're correctly noting that year is 1976 or 1978. So there's two distinct years in which this data were collected. If you ever have grouping data where you want to treat it as, hey, what group are you in? Even if it's coded up as numeric, and you can see the little blue triangle saying, I'm treating that numerically, you can adjust it to be, well, group or nominal. Tell me which category this individual is in. And that's going to be better for the sake of making the graphs and doing the various analyses appropriate. So if I was looking at, say, Graph Builder to explore whether the depth seems to be different across the different years, because year is categorical, it sort of lumps it into two categories. Now, this is a dot plot, and the way it was constructed here is it almost looks, well, sometimes they call these violin plots, but you can see the dot plot is spread out. So, more data points in any horizontal range, that means more data there. It looks as though this guy is maybe a little bit higher on average than that one. So 78 might be a little higher than 76. You might prefer the box plot. You can adjust those plots as appropriate to match your needs. So Brenna, I think that tackled your question. Yes, convert to nominal as way to go.
Thank you.
Someone else, maybe?
I have a follow-up question on that, actually.
Yeah, sure.
Why are we using Graph Builder instead of the fit y by x?
Great question. Does it matter? I can try fit y by x instead and fit y by x. Basically, as long as yours categorical, okay? Y depth may depend on x. And I see, well, the same graph, except for we haven't spread them out a little bit. It's not as pretty from my point of view. And if you were to want to sort of like use fit y by x, you still have display options. You can turn on mean lines to see that indeed it is a little bit higher on average than in this other group, but you also have the benefit of, because it's fit y by x, getting the exact means and standard deviations, or even in one fell swoop, doing the whole t-test, the regular t-test, not the pooled t-test. The pooled t-test sucks.
Okay, thank you.
Actually, I shouldn't be so dismissive about this statistical procedure, the pooled t-test. The reason it's probably in many textbooks is because the faculty members who adopt textbooks often learned the pooled t-test way back when, and so they want you to see that as well. And there is a historic reason why it was more popular, is that it could be calculated more quickly on a calculator if that's all you have. We've got GMP, we got statistical software packages. We can do fancier things than using the method, which admittedly could be calculated on a calculator a little bit more quickly, or by hand a little bit more quickly, but relies on an unfortunate and likely invalid assumption that the spread is the same in both populations. The pooled method does make that assumption, and I don't think it's a wise one, because it is usually not valid. And heck, even if you were to use that pooled method, because someone says, oh, use the pooled method, the results are almost always really quite close. The confidence interval is going to be only a hair narrower. The p-value is only a tiny bit lower. But that slight benefit comes at the cost of assuming something which may be false. We don't need the benefits. And certainly I don't want to assume false things, so I don't recommend it. Good question. Thank you for asking. Someone else for a question. I know there's at least one other.
Okay, I have a question on the homework.
Yeah.
For
Yep.
the trees problem, for the margin of error being equal to 50, the math for solving that with two different sample sizes is really complex. How would you want us to go about handling the sample size in terms of that problem?
Great question. I'm glad you asked, and I will. Can I? No, I will bump this there, and now so I'm going to write out the equation for the entire margin of error. So the margin of error, Mo, is I'm going to say T alpha over 2 times the root of S1 squared over N1 plus S2 squared over N2. And if you want that whole thing equal to about, say, capital E, a target margin of error, and if you are willing to assume that that T value for 95% confidence is not E, let's go back. I'll say it's 2. I can maybe solve for N1 and N2 is the hope, except for the problem is I can't solve for 2 unknowns with just one equation. So as you suggest, we can make some simplifying assumptions to solve. If I just say N1 and N2, if I assume they're going to be the same, take the same number of dioecious trees that are of the M variety as the F variety. And if I just say, I'm going to call that thing N, the common sample size from each of the 2 groups I've got one now unknown, and I can algebraically solve. So that's one approach. Another approach that I think is pretty reasonable is like if we consider the great blackout data. Did I mention those data in class last time?
Yes.
Okay, good. So in the great blackout data, you get 5 weekdays for every 2 weekend days. So if I said n is the number of weeks, and 1 should be 5 times then n, and 2 should be 2 times n. So if n is the number of weeks, all we have to do is solve for the number of weeks that would get us the right number of weekdays and the right number of weekend days. So there are a lot of ways of optimally tackling this problem. Most often, people just say, you know what if you're going to go with the same sample size from each group? That should get you in the ballpark of about how many data points you're going to need from each group. And if you don't get exactly the right number from each of the 2 groups, you're still going to be close. You know, if you got 27 from one group and 23 from the other, they're both close to 25. On the other hand, if there's something like with weekend days and weekdays, that ratio of 5 of the one kind for every 2 of the other kind, that ratio being pretty much fixed, allows us to tackle the problem a little bit differently. There's a fall in class, Stat 421, where we will give you details about what if you want the smallest possible margin of error with the smallest number of data points, and if you're willing to assume something, maybe you would set n1 proportional to s1 squared and n2 proportional to s2 squared. There's silly other approaches, but I think this gets after the idea that we're aiming for. So Kendall, I think that gets to your question. Did that answer your question the way you wanted?
Yes, that was great. Thank you.
Yeah, so let's get real specific about dioecious trees. If dioecious trees always come in a 60-40 ratio for F's to M's, you might want to use that 60-40 ratio like I suggested here with the days of the week. But I would probably go with that top approach, assuming male and female would be about the same. I'm just going to say, let's go get 100 trees, and that'll be 50 and 50 maybe. Okay, so let me clear that. Boom. And any other questions before, content-wise, before we jump into chapter 1? Okay, chapter 1, analysis of variance. Depending on the stat class you come from in the past, you probably did see ANOVA, but not necessarily. So ANOVA stands for analysis, AN, of, that's the O, the variance, analysis of variance. And the funny thing about the method named analysis of variance is literally we use it to see if the means are different, rather than to see if the variances are different. We use it to see if the means are different. Okay, after we present the equation and you look at it a little bit more and we wait probably until after the first exam, I can talk at that point in time more effectively about why it's called analysis of variance, but I don't want to do that one just yet. It seems like a poor choice of time or spending time. Okay. Analysis of variance. What the heck does it do? Well, let's think about it this way. What if you want to compare not just 2 groups means to each other, like with the t-test? What if you want to compare, say, 3 group means to each other to see if any of them are different? Or maybe what if you want to compare 4 groups to each other, or 5, to see if any of the 5 differ from the others? Okay. So here's an example based on an experiment done at Stanford in the late 70s. It was on diet and lifespan. And at the point in time, there was the belief that different sorts of diets would cause mammals to live different lengths of life. And so they chose 6 different diets, gave them to mice in cages, and in your own cage, you only get one kind of food, or you only get one amount of food. And we want to know, do all the population means, are they all the same? Or is there a difference somewhere between the groups? Because I guess if all the population means are the same, it would suggest that across these 6 diets, it doesn't really matter what diet the mouse is eating. It will live the same amount of time on average. If, on the other hand, there's a difference in the average length of life for the mice across, I guess, any of the diets. If one of the diets has an average that's longer or larger than one of the other diets, you'd say, okay, one of the diets is, if you will, better for the mice, and the other one might be viewed as worse from the point of view of how long they live. Okay, so I think the real question, as we learn from the T statistic, and if you flip back your notes a few pages, you can look and find the T statistic, is it compared the 2 sample means to each other relative to the standard error. How different are these 2 sample means from each other relative to, well, something that keeps in mind the sample size and the spread in each of the 2 groups, N2. So this test statistic T, you could phrase it as, hey, are the means different enough from each other relative to the spread in each group and the sample size from each group? So let's go ahead and switch back to the slide. And maybe I'll just pop it right up here. No, pop it right up there. Good. And move it over here. Yeah. I'll smallify for the moment. Just want to make sure that you can get the equation down if you want to finish that off. Okay, so how different are the means of the 6 groups away from each other relative to the spread within each of them and the number of data points from each of them? So now that I've cleared that off, I'm going to bigify so we could read more easily. And we'll go to the next slide. And boom. Okay. So if I remember the t-test from just yesterday, if I've got 6 groups, okay, I could compare diet 1 to diet 2. I could compare diet 1 to 3, 1 to 4, compare diet 1 to 5, 1 to 6. I could compare diet 2 to 3, 2 to 4, 2 to 5, 2 to 6, 3 to 4, 3 to 5, 3 to 6, 4 to 5, 4 to 6, and 5 to 6. I could do 15 separate t-tests. Wouldn't that answer the question? If my question is, hey, are all the means the same? Or do any of them differ from any of the others? The 15 t-tests that I do should allow me to tackle that question quite nicely. So what am I going to do? Well, 15 t-tests is a pain in the ass, 1. 2, yeah, I could write a program that does it. But 3, and maybe more importantly, if you remember back to that earlier stat class, you most likely talked about type 1 error and type 2 error. Type 1 error corresponds to thinking there's a difference between the 2 groups if really there's none. And we remember from that earlier stat class, type 1 error rate is always set to some level, maybe 5%. You're going to compare your p-value to 0.05. We're really saying, let's see if by luck alone, the means are different enough from each other that that difference shouldn't have been observed. A difference that large shouldn't have been seen, but for darn rarely. So if I've got a 5% rate of type 1 error, and I've got 2 t-tests, well, that's like almost a 10% rate of type 1 error. Now 3, that's like almost 15%. If I got 4, that's almost 20%. If I've got 15 separate procedures, each of which has a rate of type 1 error of 5%, the overall rate of error of type 1 variety balloons up. We're going to almost certainly think that one of the groups is different from at least one of the others if we do that comparison across the many groups to the others. What we should probably do is one overall procedure that limits our type 1 error rate. Let's redefine type 1 error rate. Type 1 error would correspond now to, hey, thinking that any of the diets are different from any of the others, if in fact all 6 populations are the same. So we got these 6 different diets, and let's suppose for the moment, all the populations have the same average length of life. And if that's the case, it would have to be bad luck that causes one of the groups to look different than one of the others. We want to set our procedure such that that will only happen, that will only claim there's a difference, that will only conclude there's a difference if we saw something so extreme that it shouldn't have happened, but for darn rarely. Okay, so I want to go back one slide. You tell me, looking at these 1, 2, 3, 4, 5, 6 dot plots, you could view them as sort of like histograms almost. Does it look like any of the groups are different from any of the others? I'll bigify here. Darn it. Make it bigger. Okay. Does it look like any of the groups are different from any of the others on average? Like 2 of you are nodding, but I'm sure the rest of you who are muted are saying, hell yeah. Okay, so yeah, I'm going to say, oh, look, this NP group seems to have a rather low mean. They die young. And this, this group over here, RR50 and NR50 and NR40, these all seem to have relatively high means. Yeah, I would think at least one of the groups has a different mean than do the others. Okay, so let's get into the procedure a little bit more in depth. What are the hypotheses we're going to use with analysis of variance? Well, if I've got 1, 2, 3, 4, 5, 6 K separate groups, my null is no. None of the groups have means that differ from any of the others. You could say they all have identical means, but I would just say if mu1, 2, 3, 4, 5, and mu6 are all the same, you could say they're all with the same mean. The logical opposite of the null hypothesis is your alternative hypothesis. So the alternative hypothesis here is not the previous set of equalities. That means at least one of those equalities is a not equal to. Maybe in better plain English, at least one of the populations has a mean that differs from the others. Or you could phrase it, at least 2 of the populations have means that differ from each other. So all the same? No, not all the same. I guess the alternative hypothesis here says that at least one of the diets is better or worse than the others. So what about a test statistic and a p-value to conclusion? Well, I'm going to do this in slightly a different order. I'm going to maybe... wrong button. There we go. I'm going to say, let's just show you how to get your answer from a p-value. I'm going to show you how to do the procedure, and we'll sort of look at a test statistic in that's vague and general sense, and then we'll get around to defining it by the end of class today. But for now, there we go. But that's the wrong data set, and here's the other wrong data set. But I've got my data here on our friendly lengths of life for the different diet groups. Okay, so what we learned recently is under analyze, fit y by x. It does t-test for us. Let's see if the lifetime depends on the treatment. And I'm really reading that out in sort of a plain English way as I slot variables into the positions. I'm saying, does y depend on x? Does the lifespan depend on what they eat? And I'm going to click OK. Something will happen. Oh, look, I get data that are, well, dot plotty. I could, if I wanted to jitter them around a little bit under display options, I could sort of spread them around. And you see that, well, yeah, there's a lot of data where this group here a little bit lower than these other three that are closest to it. Okay, we learned, okay, go ahead and do another method. Now notice that there is no more t-test option. Because there's 1, 2, 3, 4, 5, 6 multiple groups, not just 2 groups, but more than 2 groups. It says, we know you don't want to do a t-test. Here is the list of things that we think you might want to do. Maybe tell me the means and the standard deviations from each of the groups. So, mean, standard deviation, and maybe an individual group, average, okay, or I guess standard deviation is shown here, a range of plausible standard deviations. You could maybe with a confidence interval under display options, I could show you mean CI lines. The confidence interval that we talked about yesterday, we could display those. We're 95% sure that the low protein mean is in that range. The N/N85 is in that narrow range. NR40, the mean is, these are horrible names for diets, aren't they? If you saw an ad for the NR40 diet, would you ever say, hey, sign me up? Probably not. These are just names that we gave the diets for the mice. But I'm spotting a couple. These are high averages. This one's quite low compared to all of the others. I'm thinking pretty much at least one of the groups is different from the others. Let's see, because we're in the chapter entitled ANOVA. Let's see if the means ANOVA procedure tells me an answer, okay? It actually slots in here some little diamondy things. Maybe I should turn off the mean lines that mean confidence interval lines that I had earlier. Let's remove the mean CI lines. And we're left with, again, these confidence intervals showing for each of the individual groups. But down here at the bottom, we see, okay, the means and standard deviations, again, means and standard errors and sample sizes. But we have, oh, look, a p-value. With a p-value of tiny, what do you conclude? And here's where I'm thirsty, so I'm going to take a drink of water while one of you unmutes and tells me what you conclude if the p-value is below 0.05.
We can reject the null hypothesis.
Yeah, reject the null. So what null did we reject? We rejected the null of
That
the
all
population means we're all the same. Perfect, Anna. And so what does that tell us? Well, at least one of them is different than the others. Now, I guess that's our conclusion. Reject the null, believe the alternative. If we're working with plain English, you'd say, aha, at least one of the diets is better or worse than the others from the point of view of average length of life. We did skip over one step, though. It's the calculation of that test statistic. I didn't do a t-test. I somehow just jump right into a p-value. A test statistic generically is a way of measuring how closely the data match the null hypothesis, or if you will, how far away from the null hypothesis the data are. I mean, I guess if I use a yardstick, a tape measure to determine someone's height, I could say how close to average is that person's height, or I could say how far away from average is that person's height, right? Same thing. But the measuring device, that yardstick, or that better yet, tape measure, would allow me to measure that thing. Our statistic here, let's see if I can recover that. It's called F. This F ratio is your test statistic. And the point of the rest of class today, and the point of the lab activity, is to sort of walk you through the thought process behind that F ratio, and to get you to understand a few things about it. But I'll say that admittedly, with just one day in class, plus one additional asynchronous day working on the lab, we only sort of start to develop our understanding of the F ratio. We'll continue that understanding into the next many weeks. But I'll just say for now that F ratio is what we're going to aim for. And I'm going to start down the path of looking at our t-test, which I put upstairs. And the F ratio, I haven't defined the terms just yet, okay? But let's look at the t-test is how far are the sample means apart from each other relative to stuff with N's and S's. How far apart are the sample means from each other relative to the spread within each group and the number of data points from each group? That same way of thinking is in our F ratio. Now, this thing SST, we'll talk about in a little bit. It's on the previous slide. It's going to be divided through by, well, stuff that involves how widely spread the data are in each group and the number of data points from each group. Let's get after this friendly SST. It is a way of measuring how close the group means are to each other or how far they are from each other. We have to consider what the heck the group means should look like if the null hypothesis is true. The null hypothesis is yeah. All the population means are identical. And if all the population means are identical, all the sample means should be really close together, yeah? And I can't really compare each sample mean to each other sample mean so easily as I could compare the sample means to, if you will, the average of all of the data values. This number of y bar bar in the equation, sometimes it's called the grand mean. It's the average of all the data points that you got in your data sets. It's the average length of life of the mice in your experiment. And I could compare the low protein average length of life to the average length of life of mice. I could compare the N/N50 length of life on average to the average length of life of the mice across the whole data set. So I'm looking at this thing here where I'm saying, let's take each group, compare it to an average, square that. That looks like a standard deviation squared calculation. If you remember that other past stat class from earlier in your life, remember the difference of something from an average squared and then summing it up? That's like a standard deviation. So this looks like we're summing across all of the groups, group 1 up to group K, the number of data points in that group, how far away is that group's average from the average of all the data points across all of the groups, square it, and SST will be that natural measure. Why would it be natural? Well, if the null hypothesis is true, and let's imagine like the worst case scenario. I mean, what if all of the data values have, well, I guess across all the groups, the averages are all the same. If every single one of the 6 groups has the average length of life of exactly 30.0, if every single group mean is 30, and the grand mean, shoot, that's the average of just all the data points, and the average across multiple groups, all of which have the same average, that will be the same. Each group would not deviate from the grand mean, the average of all of them. I'd have a bunch of zeros all squared. So even if I multiply by a number and add up a bunch of them, SST will be 0 if the null hypothesis is perfectly true in our data. In most cases, it won't be exactly 0, but I'll just say SST will tend to be small if the null is true, at least by comparison to what about in our case. Let's look at, go back a couple pages. Here, it looks as though the means are way all over the place. If the group means are sometimes far from average across all the data points, we'll have a big difference squared, which bigifies the even big. And I'm adding up a lot of large values. If the alternative is true, one of the sample means will be higher. Another one of them will be lower. They'll differ from the grand mean, and we will find that SST tends to be big if the alternative is true, small if the null is true. Let me show you where to spot SST in your JMP output. Do y'all see these columns called sums of squares? SS is for sums of squares. T for treatment. Our friendly SST is right here. So the question is 12,733.942. Is that small or is it big? I mean, I just told you that if the null is true, that number is going to be small. If the alternative is true, that number is going to tend to be big. Is that 12,000 small or is that 12,000 big? That's sort of a tough question, isn't it? Okay, so that's like working with these really unusual units that every so often you get in a physics class, like foot-pounds per fortnight. Seriously, if you express that on the test and give me, conversion of foot-pounds to like metric units and fortnight, shoot, that's 2 weeks. Let's convert that into per second. You can get an idea by rescaling your unusual number, how many foot-pounds per fortnight. Is that a lot or is that tiny? I don't know. But if I rescale it into units that I could work with, I can better understand what to do. It's almost like you take that ruler and you take it from the side that has like inches and flip it over to metric, which makes it easier to do the science. In that same sense here, we are going to be recording, not recording, I just read an email from someone with the word recording in it. You ever have ADHD? Okay, so I got distracted. I probably should adjust the do not disturb mode so that way I don't have text flashing in front of my and emails flashing in front of my eyes during class. Okay, so let's convert SST, which has these goofy units, into at least something which makes some sense. That is the process here that we suggest. We're going to take this SST number and standardize it. And we're going to standardize it so that way the F ratio, the ratio of SST over stuff, is about 1 or smaller if the null is true. And it tends to be much bigger than 1 if the alternative is true. So that F ratio, just think small when null, large when alternative. What would a value of null hypothesis being true be like? Yeah, about 1 or so. A lot smaller than 1? Well, don't doubt the null hypothesis. A lot larger than 1? Yeah, definitely doubt the null hypothesis. Let's go a little bit deeper. And I want to skip this slide for a moment. I want to just dive right into a notational style our textbook uses, and that is the word equation. The word equation. It's not literally an equation, but because there's an equal sign, they say the word equation is the word equation. Okay. The word equation says what's on the left depends on what's on the right. So let's just say length of life depends on diet, or length of life might depend on diet. If I said, and this is something you'll see in the lab, if I say your score depends on which handicap you appear to have, that would say score is depending on, or maybe score doesn't depend on handicap, but the word equation behind the analysis is score equals or depends on handicap. We want to see if that's the case. Back earlier in the homework on the dioecious trees, you tackled the problem, does the number of flowers depend on the sex of the tree? A word equation. So a word equation is just the way we say things, and our authors start in chapter 1 to really dive into that path. So I want you to see what it is before you get, more complex versions of our friendly word equation. Okay, so here's how to get after it. And really, ANOVA is just our way of seeing if across more than 2 groups, actually you could use it for just 2 groups, but across the groups you have, is the mean different across any of them? Okay, and you're going to sort of use your method that our book will sometimes call the general linear model. And we'll see that that's the name we'll give chapter 1, ANOVA, and a chapter 2, regression. Once we hit chapter 3, anything that matches a word equation, like score depends on handicap, is going to be within the general linear model context. And so analyze fit model will get you the ability to do that, at least for the first few chapters. Then we'll use a slightly different, then we'll use, because fit y by x works at first, then analyze fit model, okay? Okay, so let's consider how close these individual green group means are to the grand mean shown here in gray. The none group doesn't appear to differ much at all. Crutches seems to have the highest difference with the largest difference from the mean. Hearing loss, and this is a preview of the lab activity, hearing loss is the greatest below the mean, but it's fair to say that each of the individual groups has a difference from the mean. That difference here, once squared, I'll just put a little dot there because it's hard to really even show it. So these little red distances all summed and squared. So get you SST. The larger the group's average differs from the average across all the data, the larger SST will be. But there's another way of looking at the variability of the lengths of the mice. Let's actually look at. I'll go with blue. Compared to the grand mean, each of the individual data points has a difference from the grand mean. Heck, all of them do, not just in the first group, in every one of the groups, and that sum of the blue guys squared, and that's called the sums of squares total. SSY is equal to the total sums of squares. It's a measure of how far are the data points apart from each other. I'll show you that in a little bit. Well, maybe I could do it. You might have spotted in our analysis, and I'll get back to the earlier slide very shortly, but you might have spotted, oh, darn it. You might have spotted sums of squares, between the groups, sums of squares due to the treatment, SS, if you will, total. I'm sorry, SST between the treatment groups. The sum of squares total, that's the 28,000. So the total spread, blue spread, is that 28,000. Our SS total, that's the red thing we got going here. It's how far are, not total, but between the treatment groups, how far are they away from each other. But let's go with green, third way of measuring spread of the data. And I'm going to use green because it corresponds to how far are you away from your group mean. So let's go with this, this hearing group. Y'all spot that each of them also has a difference from its individual group mean. So we had, that data point compared to the average. But it also could be compared to the average of its group. Every data point has two differences. How far away is it from the average across all the data points, blue? And how far is it away from the average of its group mean, green? Now I'm thinking the variability in total as expressed by this equation, and I'm not going to show it to you, that's sort of for a different class, but the variability blue is equal to what we have as red variability plus green variability. And the spread of the data within the group, that's like measuring a standard deviation. We literally could take the standard deviation in each group and square it and sum it to get SS error. We have to scale it up a little bit, but we have an equation that relates the standard deviation from each group to SS error in total. SS error of the data points around their group mean, if you will. Okay, got 3 minutes to go. I'm gonna screenshot that. If y'all ask, I can put that online, and I'm gonna clear and then move forward with one last thing. Our ANOVA table, and I'm going to probably start in on this tomorrow as well. The ANOVA table is historically just a way of keeping track of calculations, but it today tends to be something that you present the whole of anytime you have multiple groups that you're comparing. So if you do a comparison of the means across 6 groups, you got to present the ANOVA procedure, all of the ANOVA table. That's just standard way to do it. Okay. What about the first thing I said, which was like, oh, it's historically just a way of keeping track of the calculations. Okay. If I were to go back several slides, notice that there's a lot of calculations here in this denominator. There's like the individual standard deviation is a square, and then the spread of the groups with the. Okay, so that's a lot of content to keep track of. And the guy that invented the analysis of variance procedure, okay, R.A. Fisher, he did his work at the Rothamsted Experimentation Station in the UK. He did his calculation work at night by an oil lamp or candlelight, that sort of thing. Now, if you're doing lots of sums, will that be hard to keep track of all the different everything? Could you just do it on your calculator one fly now? Yes, you probably could if you punched the numbers in correctly, like some of you were taught to do in high school. But if you remember that physics problem in high school, where you had to do like one whole page of calculations to summarize one aspect of your experiment, and then another page of calculations to summarize a different aspect of your experiment, then a third page of calculations for some other number, then a fourth page, then on the 5th page, you took all the first 4 individual numbers, like at the bottom in the lower right corner of each of the previous 4, and then you put them into a new equation to get your result. Y'all remember that sort of thing in physics once? I hated that. Yeah, the ANOVA table is just that. You could view it as a lot like Excel, that literally, if I looked at this ANOVA table, okay, it's going to keep track of all of the calculations necessary to get my F ratio. We're going to pull it apart in greater detail next time. So far, what you do know is the sums of squares across the groups, across the handicap groups, is what you're going to be looking at in the lab shortly. That's a measure of how spread apart are the groups from each other. If that's big, which happens if the null is true, or null is false, the mean square should be large if the null is false, which means the F ratio is going to tend to be large if the null is false. These other things in the sums of squares, they are like we had earlier, our green variability of the data points around their group mean. That's for like a standard deviation. It ends up in the denominator of the F ratio. Notice that 7.6 over 2.7 is about 2.8. This mean square column is the way you get from the sums of squares and degrees of freedom to that F ratio. More on that next time. We're gonna, I gave you an equation with the lab. I don't think you're gonna have to use it a lot, but you might want to remember SST, okay, spread between the treatment groups. That is really your friendly key. Okay, it's 5:01. I think it's time to be done. I'm done, but heck, I will stay around for a little bit longer if you got additional questions. So I'm happy to answer. If you don't have questions, that's fine too. There will be a recording later. Okay, so I just an aside comment now that some people have left. It's not going to be anything that the rest of you would really care to hear. You know, if you leave or don't leave, no big deal. It usually takes 2 full days to grab onto ANOVA in the way that we're doing it. The lab super helps with some of what we talked about today. And then as we finish it up tomorrow, you're going to say, okay, it still is a little challenging, but as we go through the term, you'll be happy with it. As we go forward, every single step, you're going to be a little bit happier with the path that you're on. Okay. So if you feel like, oh my gosh, he just shouted algebra and calculations at me for an hour, that would not be an unreasonable feeling. It's the thing that the lab clarifies, and we should be just fine in the very near future. So I'm going to stop the recording and the sharing shortly, but I'm still tackling questions. Anyone got one?
Just to clarify, the ANOVA lab is due tomorrow night at 11:59.
Yeah, the one that you could start on now with your group mates, because I've gone over enough of the content that you could dive in. And again, like the first lab, it sort of leads you through step by step and gives you some suggestions. Here's how to get the calculation done. It asks you these leading questions and shows you how to do it. That plus a lecture type thing usually gets people to be ready for the next bit of material, which is tomorrow at 4 p.m.
Okay, thank you.
I guess what I just said is, if you do it before tomorrow at 4, you'll be a lot happier than if you wait until tomorrow after 4. So Kendall, I saw your kid walking by, or maybe not walking, but the head and whatnot. You should introduce him or her to everyone at some point in time in class.
I can do it right now.
I will stop the recording first, though. Okay.